All right, so today's topic is block ciphers, and we are going to talk about three important ciphers: present, des, and AES. So actually, almost everybody starts with des because it is the oldest, and people still think that it is important. It is no longer used, but we use it in triple des. But lightweight algorithms are simpler, so it is easier to understand. This is why I prefer to start with a IOS standard for lightweight block ciphers, that is present. So let's talk about present. So in this category, there are three lightweight block ciphers, three standard lightweight block ciphers for ISO. So they are present, Cipher, and Leia. So I'm going to only talk about present. I think it was, it was, as you can see, published in CHES 2007, but around 2009, if I'm not mistaken, it became an ISO standard, and it is still in the current standard. So this is actually a ISO standard for lightweight crypto. And lightweight, we say lightweight because we are focusing on here on the small devices like limited capability, limited memory, battery power, and so on. So you want to design something secure, but also really fast and good for some special architectures or environments. So the algorithm is really simple. This is an SPN cipher. So there are three layers: key addition, substitution, and permutation. So in one figure, we can see the one round of the cipher. So if you repeat this figure 31 times, put one to the below, and at the end, at final key addition here, then you end up with present. So let's look at the characteristics. These are really important, by the way. Some people think that it is something to memorize, but actually you shouldn't memorize them. You should know them by heart because it tells a lot about the cipher. For instance, key length. It supports two key lengths, depends on the user choice, 80 bits and 128 bits. This actually shows you your security, right? So it is good to know. Block size is 64 bits. So I have 64 lines here, all of them representing a single bit. So this actually shows the size of the data that you are going to encrypt. And this also affects your throughput and so on, because this tells you that you encrypt 8 bytes by 8 bytes, right? Because 64 bit is 8 bytes. So these characteristics are important. So let's start. Your plain text, just assume that it is 64 bits. So you write zeros and ones here, your plain text. Then you XOR it with the round key. So we will talk about round key in the next slide. So assume that we chosen the secret key as 80 bits, but from this 80 bit, we generate 32 round keys, which we use at these points, okay? And round keys are 64 bit, not 80 or 128. This is the important thing, because here I'm XORing the input with the round key, so their size should be identical, right? And this is why, since the block size is 64 bits, round keys are 64 bits. So round keys doesn't have to be at the same size with the master key, okay? All right, so after key addition, we have substitution layer. So here we have an S box which takes 4 bits as an input and 4 bits as an output. Okay, so all of these S boxes are identical. We have 16 S boxes, and this S box is represented here. So it tells you which 4-bit goes to which 4-bit in the hexadecimal notation. So assume that your input is all 0. Okay, so assume that you have 4 bits, that is 0, 0, 0, 0. So in hexadecimal notation, it is 0. And it tells that the output should be C. So C is 12 as integer, but as bits, it is 1, 1, 0, 0. So this is the confusion part you use. So you do it for every S box. Then you have to perform the permutation layer. So this permutation layer just changes the places of the bits. For instance, this bit, its place doesn't change and goes here. So in the next round, it will still come from here. But this bit will go here. So in the next round, it will be coming from here. So this is the diffusion part. Okay? Very simple design. Even you can implement it just by looking at this figure. But of course, it will be hard to detect which bit goes to which place. So you have to actually have a table that is in the paper where you see which bit goes to which place. Okay? So we almost talk about everything except the key schedule. We don't know how these round keys are generated. So let's focus on the 80-bit key. So you choose a random 80-bit key. Okay, so these are random zeros and ones starting from. We say that the rightmost is represented as K0 and this is K79. And round keys are the leftmost 64 bits of this master key that we keep in register. Okay, so if you have an 80-bit key, here the first round key is the leftmost 64 bit of it. Okay, as you can see here. Then we will perform some operations on this master key to choose the next round key, which will be again leftmost 64 bit of this master register. Okay, so this is your key I. Then you update this master key register K as follows. The rightmost bit now becomes the 19 bit. This means that actually right rotate everything 19 bits. Okay, so you take the rightmost 19 bits and put it to the left part. Okay, this is how you make the rotation. I will also show it in a picture by the way. But this just says that right rotation of 19 bits. Okay, then take leftmost 4 bits and apply the S-box operation to it. Then these 5 bits are XORed with the round counter. So what is round counter? Round counter is actually the number of the round you are currently in. Initially it is 0. In the first round it is 1. In the second round it is second. So at the end you will be at the 31st round. So it will be 31st. But since we are XORing, think about 31 in the bit notation. It is just 5 many ones. So you will be XORing it with these 5 bits. Okay. You can ask later or now. So the round counter is actually just XOR. So you might also ask, why do I have a round counter, right? Actually, it's just trying to break the symmetry because every step is identical except the round counter, because in the first round it is 1, in the second round it is 2. Okay, this actually prevents some kind of symmetry attacks. Okay, so let's see how this actually applies in picture. So you have an 80-bit master key. Okay, so leftmost 64 bits is your round key I. Then in the following round, you will use again the leftmost 64 bits. But before that, we have to modify this 80-bit register. So as you can see, we take the rightmost 19 bits and put it to the left. Okay, so this remaining part comes here. Once you make this modification, you apply the S-box to leftmost 4 bits, which weren't actually these 4 bits. Actually, they come from here, by the way. You also add the round key in the XOR operation to here, to these 5 bits. Okay, so you actually modify this 80 bits in a very simple way, then use the 64 bits as the next round. So you will keep doing it 31 times. Okay, I will talk about key schedule 128-bit, then I will give an example how these operations actually work. Okay, so let's look at key schedule for 128-bit key. Now you have 128-bit key. As I mentioned, algorithm supports 2 key lengths. You can either choose 80 bits or 128. So if you choose 128, you do a similar operation. This time the round keys are again leftmost 64 bits. Then you rotate this 128 bits 67 bits to the right. Okay, in the previous one it was 19. Now your rotation number is 67. Then you apply again S-box to the leftmost 4 bits, but now you also apply the S-box to next 4 bits. Okay, then you add the round key. So it is almost identical. There's only one more S-box operation. Okay, so let's see it as in an example. Assume that I want to use present with the 80-bit secret key. Okay, so I choose my secret key as 80 zeros. So in hexadecimal notation, it says represented 20 zeros here, right? 8, yeah. So there are 20 zeros, but they represent 80 bits. So recall the algorithm. It said that take the leftmost 64 bits, and it will be your first round key, right? But since it is all 0, leftmost 64 bits are also all 0. So my round key one is 64 many 0 bits. In hexadecimal notation, of course, there are 16 zeros. So this actually, as you can see, there are less zeros here than this. Now recall the operation. We focus on the master 80-bit key and perform operations. Recall that the first one is to right rotate it to 19 bits. But if something is all 0, it doesn't matter if I rotate it or not, right? So it's still 0. Remember the next step. Apply the SBox operation to leftmost 4 bits. Leftmost 4 bits is 0. Recall the SBox operation. When the input is 0, the output is C. Right? So for this reason, the next round in the leftmost 64 bits become just C and all zeros. This C comes from the SBox operation. So if I go back, it is because of this, or in the figure this. Okay. So at this point, my master 80 bits become actually C and zeros, and also the XOR with the round key. Next, recall that I have to rotate it 19 bytes to the right. So this C actually will come someplace like this. But recall that C is 1100. If you rotate it 9 bits, so most probably it will become affect 2 characters here, like 1 and 8 or something. Then I will also add the round key, so it becomes like this. Okay. If you keep doing this, your round keys become, as you can see, the diffusion and confusion is not that good. We started with all zeros. We still see many zeros, right? It doesn't look random, what I mean is. So if you continue this way and create all of the round keys, as you can see, the final ones looks better in terms of randomness. But here you have a lot of zeros. So this is your key schedule. So when you implement an algorithm, you can use this as test vectors. What you need to do is to implement the algorithm and use this table, choose the master key as all zeros, and see if you also see these round keys when you print them on the screen. If not, this means that you made an implementation error. And it is very easy to make an implementation error, especially when you work on bits in a cryptographic algorithm. Okay. So if this is the key schedule, then what happens when I encrypt something? So if I use this master key, let's give an example. I choose my plaintext again all 0, 64 many zeros. I also choose my secret key as all zeros. And let's see what happens. Actually, we can go to the figure and actually see what happens by ourselves. Okay, let's go back. Here, I have all zeros here as the plaintext. My master key is all zeros, so first round key is also all zeros. If you XOR 64 many zeros with 64 many zeros, you end up with 64 many zeros here before the SBox. If you apply all of the SBoxes, as you can see, input is always 0 and the output is C. So you end up with C, 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 etc. until here. So actually, if you look at it in terms of bits, what you have is 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and this goes like this. Next step is the permutation. And this permutation is chosen in a way that the rightmost 2 bits actually stays on the right part of the cipher, and the leftmost 2 bits of an SBox output goes to the left part of the cipher. We can actually see it if we can follow the lines correctly. Okay, for instance, look at this. We have 1, 1, 0, 0, right? That 0 goes here. This 0 also goes here. So in the second round, it will be coming from here. But we have 1s and 1. This 1 goes to here. So what I mean is that if you divide the cipher from the middle, 1s always goes to these parts and 0s goes to this part. So after the permutation, what you will end up with is 32 many 1s here and 32 many zeros here. Think about it in hexadecimal notation. You end up with many Fs and zeros. So this is why if you encrypt this plaintext with master key as all zeros, the first round output is 32 bits of 1s and 32 many zeros. In hexadecimal notation, it becomes Fs and then zeros. So you keep doing this. This will be your round outputs. Okay. As you can see here, the diffusion and confusion is better. Even in the small rounds, some values look random to us. If you continue in this way, your 31st round output is this. Then you XOR it with the final round key, and this is your ciphertext. So this means that if you implement present algorithm correctly, when you use the input as all zeros and the master key as all zeros, this will be your ciphertext block. Okay, so this is how present algorithm works.